left foot forward, right foot backwards. And move it off, just move it.
Okay, you supposed to sit down, and then I'll introduce.
Oh, see it. All right.
Welcome to the Strategic Engineering Colloquium Series. Today we have essentially one of our own speaking to us today, Dr. John Mihalczo. He got his BS and MS from New York University and his PhD from Tennessee. And I might make a comment that when John came here, he already had more journal publications than the entire rest of the faculty put together. And so that's the way you want to be as a graduate student, is you want to have more publications than the whole faculty put together. And he has not stopped. He's continued to be a prolific publisher, and he's also a corporate fellow, first at Martin Marietta, and I guess the Oak Ridge National Laboratory, you'd say now. And so we're very pleased to have. I might also mention that John and I taught the lab together for a number of years, and he's done a lot for this department. He's taught here for many years. He's directed the work of many students. He's provided a lot of financial support, and so we owe a significant debt to John. John, would you go ahead and get started?
What I'm going to try to describe is some experiments done in the east cell of the Oak Ridge Critical Experiments Facility. Most of these experiments were backup for criticality safety, not backup, really the primary data used for criticality safety in a Y12 plant. At that time, in the late 50s and early 60s, nobody believed calculations, and a lot of times they didn't even do them. Okay. The whole criticality safety department in Y12 at that time consisted of 5 people. And the plant was running at a rate like factors of orders of magnitude more than it's doing now. So whenever they had a problem, they just call over the hill to us, where we had this great supply of highly enriched uranium, and say, hey, put this together and see what happens. Some of the things we tried to put together remotely, we had prompt criticality accidents, but that killed the design of a certain kind. So I'll go ahead and review the experiments. They're not in chronological. Now, they probably were documented a little more than most at that time, because the previous 5 years before I came to Oak Ridge, I worked in doing calculations. And I was trying to calculate experiments, and I never could find out what the experiments were, and they didn't tell me where the elephants were standing nearby this bare, unreflected assembly. And so you never could get the right answer, so I finally said at that time in my career, well, I'll just go make the measurements and do the calculations too. So we'll start. The first set of experiments that were going on at that time when I came in were 2 and 3% enriched uranium, UF4 mixed in paraffin with various hydrogen-uranium ratios, and this was to support the criticality safety work that was needed to do for the separations plants, both originally here at K25 and then at Paducah on the low enriched end. And so I'll describe some of these experiments. I'm going to go through these things rather quickly. I've got a ton of slides, but I just want to give you an overview of the kinds of things we did. These are UF4 paraffin blocks. This is a horizontal assembly machine. Let's see, I'm going fast. Each half of the assembly was built on one half of a table. One part of the table was movable, and you just pushed it up until they were adjacent and achieved delayed criticality. Now, here's a picture of the stack of blocks. They stacked together really nicely. It was a real careful fabrication by the Y12 plant. It's basically UF4 paraffin, and paraffin, as you know, is like a wax. And they were coated with a thin layer of less than 1,000th of aluminum foil, which was sort of ironed on them. A little more complicated than that, but basically. And that kept the green stuff from getting in our hands. Okay? This material is green, and so here's a picture of 2 halves of the assembly. Now, whenever we did experiments, we tried to evaluate the effects of the support structure. And so here you see on the bottom, how's this work, Gary?
You gotta double click at the mouse.
Double push the right?
There's a button on the very bottom.
Oh, okay. That works. So we would mock up the support structure on the bottom by additional support structure on the top to evaluate the reactivity effects and try to correct the measurements for presence of nearby materials. Here's a big concern in assembling unreflected assemblies is the effect of moderator, because you've got to go up there yourself and put the next set of blocks on. And you don't want to prompt criticality based on your body reflection because you're dead. Okay? And so there are a lot of experiments in evaluating moderators. And here you see a piece of moderator being pushed up against the assembly. In most experiments that we did unreflected, we tried to do some kind of simulation to assure that when we went up to put the next pieces on, we were going to be okay ourselves. Here's a photo of some foils. We did a lot of basic physics measurements. These are cadmium and uncovered cadmium foils to determine the ratio of cadmium covered to uncovered flux. Cadmium has a cutoff of about a half an MeV, so when you put the cadmium cover on, you detect things above a half MeV. When the cadmium cover's off, you detect everything. So it was a kind of a spectral indices. We did foil traverses across the assembly, and here you see some counters that were moved horizontally to measure the flux as a function of position at various heights in the assembly. So we basically did a 2D measurement of the flux along the center of the system. This is a measurement. We wanted to find out what K infinity is for this type material, and so we did some height perturbation measurements at Oak Ridge and did some little theory to come out and show that you can get the infinite neutron multiplication factor. And then we sent the blocks off to Hanford to what was called a PCTR, which was a graphite uranium assembly, which was basically around the test sample region. And so what you put in the test sample region is the blocks of interest to tailor the spectrum to be correct between the graphite uranium assembly and the sample, which you put in the middle. And so all this material around is to tailor the spectrum. And then by substitution measurements in here, Dr. Neely could determine the infinite neutron multiplication factor, and so we made comparisons to the Oak Ridge data, and everything agreed quite well. A photograph here, I don't know if you can see it. Maybe we should put the lights out. We did pulse neutron experiments at that time with a 150 kilovolt Cockcroft-Walton that was really difficult to keep operational. It basically required one PhD physicist working full-time to tune everything and keep it working. So you put pulses of neutrons in and observe the time decay. You could even do this in critical assemblies. You would raise the level by the pulse, and then it would the prompt neutron decay would go down, even though the system was at delayed criticality. Now, we did a lot of experiments for basically in this cell for criticality safety for highly enriched uranium. And they first started out with metal slabs. The uranium metal slab is a 8 by 10 inch, 1 inch thick, was the standard casting at Y12. When they first made uranium metal from the material coming from the diffusion plant, they cast it into 8 by 10 inch slabs. And here's a photograph of some of the material hanging on aluminum rods on this horizontal table assembly. Now, the horizontal table assembly didn't separate very fast, so we were a little squeamish about getting too close to criticality with these systems because we didn't have a real good shutdown mechanism. So we did multiplication measurements to try to determine what the critical mass of the slab that was the standard Y12 casting was. And we did slabs with areas as big as 24 by 25 inches, and critical mass is estimated up to 300 kilograms. Now, we didn't assemble those at 300 kilograms. We probably went to the order of 200. So we're dealing with substantial amounts of highly enriched uranium. As you know, the reflected critical mass of uranium is, with water, is 22 kilograms, and the bare critical mass is 55. So when you're dealing with these kind of quantities, you've got to be real careful. The next experiment was the one that I couldn't believe I had responsibility for. It was one of the first experiments I did. Y-12 was storing these castings on 3-foot centers in a plant, and we're running out of storage space. And so they asked us how much closer we could put them. Okay, so we said, we'll find out, just send us some. And to show you how fast things got done in those days, that kind of a decision was made on a Thursday, and on Monday the material was coming over the hill to the facility. And so here, and the first concern was, can we get it off the truck and into the room safely? Okay, and so we had, I'm going the wrong way, sorry. We had these storage shelves on the side of the room, and what we would do is, background there they are. We would unload from the truck and do a multiplication measurement. And so we tell the truck driver, give us one more and shut the door and go behind the concrete, and we'll make a measurement. There was a concrete wall outside. And so as we unloaded them into the room, we got a total of 125 of these, which is 2,750 kilograms of 93% enriched metal. 2 of these systems on the floor, one on top of each other, 2 of these slabs, is real trouble. It's 44 kilograms side reflected with hydrogenous material. So what we tried to do was build up arrays of these things on little unistrut frameworks. Here's a picture of one of our co-workers, and a 3x3 array, half on one side of the table and half on the other. And again, this is a multiplication measurement. Here's a counter here and here measuring a count rate from a source in the center of the assembly. And then we went to the 5x5x5 array, and that means all 125 pieces. And what we did is we started at large separations and worked inwards towards smaller separations. And what you see here is the smallest separation. The slabs are on 1-foot centers. And put the 125 slabs inside a 5x5x5 foot cube with an inch of plexiglass around it. This made Y-12 quite happy, and it relieved a lot of their concerns about storage, and so they could come down in the amount of space required to store a given number of items. We had one rule in the experiment was, well, never assemble something by hand that you hadn't assembled before, remotely, and the other was, don't be moving more than one slab at a time, because if 2 people walk past each other and both drop them on the floor on top of each other, then those people are gone. Here's a close-up picture of the array. The slabs were castings. They were in polyethylene bags, placed in little trays, and they had in case the trays broke, we had this little aluminum or steel support underneath it so that this part wouldn't fall down on top of the next one. And this is just a unistrut framework built out of nuts and bolts, and you put it together yourself, and rather simple, and worked effectively. Here's an experiment we did in the mid-'80s. They came along and designed a storage safe and said, actually they had the safe, and they said, we want to put 24 of these uranium castings in it. And it had a 3x8 array to take these 22 kilogram castings. And here's a picture of a horizontal assembly machine where we were putting these together. Again, putting them together remotely before you load them by hand. And notice that in the remote assembly there's a big piece of moderator back here that simulates the person who's going to put the material into the safe. Well, the outcome of this thing was that this had borated plaster between layers, between positions. It turned out if the boron came out, K went up to 1.15. If the hydrogen came out of the plaster, K went up to 1.15. If the plaster wasn't there, it was subcritical, and if it was flooded, it was also subcritical. So that put this safe to rest, and I think it went away forever. A little close-up of it, and here you see the little receiver for the slab, one on the bottom and one on the top, so to get it in there correctly without misaligning it. Let me go on now to critical experiments. We got this vertical assembly machine, and it was an interesting piece of apparatus. It had two halves, an upper half, which something fixed was supported on, and the lower half. Well, this was a machine designed to rapidly remove material. In fact, you could exert through the hydraulics the forces of like 5G on this table to go down for a short while, not to the bottom at that level. Well, so we started playing around with it and not thinking very much. We put some bricks on there, lead bricks, and said, well, let's just scram it at high pressure. Well, we did. The table came down and the bricks stayed up in the air. Then they came falling down all everywhere. It just shows we just weren't thinking. So we did a lot of measurements with delayed critical experiments with uranium on this type of apparatus because we felt it was safe and designed for that job. So now I'll describe delayed critical measurements. Again, we took these 8 by 10 inch slab pieces that we had and we assembled them to delayed critical. And the top half supported by a 10,000 stick stainless steel diaphragm, and the lower half pushed up remotely, slightly lifting the diaphragm until it was level, and then monitoring what was happening until we got the delayed critical configurations. Next, we performed this measurement with an annulus at the top half, again supported on this thin diaphragm, an annulus with a piece of metal across the top. And then the next part shows the bottom half of the annulus with a void in the interior and, of course, metal on the bottom, supported again by a very low mass support stand. If you scram this system, this support stand would bend. You have to put another one on it. But we wanted to keep the mass down because we want to try to do clean experiments so we could have a good basis for checking and calculating. Now we looked at interaction, which is a big problem in Weiss Holding storage. You have two things next to each other. How do they communicate via neutron? So the first experiment we did was with the varying diameter cylinders, 2 cylinders. We first assembled a system with a cylindrical geometry of a solid cylinder, okay, and then we started adding more material, always keeping half on the bottom, half on the top, and determine the criticality separation. We stacked to quite high K effectives on each half, and the next slide shows how that could be done safely. We had the upper half here, and you would remotely lower this plate. You stack this much by hand, and we stack things by hand to Ks of somewhere between 0.95 and 1. An interesting area to be in. Always concerned about body reflection and handling. These were always systems, whenever you're putting material on these systems, you're always putting it up over your head so that if you fell away from it. Same on the bottom. You stood on the floor, your head was about this height. And so here we have the 2 halves, and the system is assembled by lowering the top half and then raising the bottom half. And what we did is we adjusted the spacing by adjusting the position on these vertical poles that supported these 2 support stands. Now, Robert Elwood did a great job of benchmarking these types of the 11-inch diameter interacting experiments in the solid cylinders for master species. We also did 3 interacting cylinders. Let me go back again to the 2 for a minute. The largest system we ever assembled was 2 15-inch diameter cylinders with 164 kilograms in each half, spaced 1 meter above the other. So if one fell on the other, you had 320 kilograms together. Okay? Probably wouldn't be allowed to do that measurement today. So here we did 3 interacting cylinders, and Richard Taylor has agreed to try to get these in benchmark form. We know the information about these systems to quite high precision. If you look at all the uncertainties in K effective, you come out to probably about 0.0006 uncertainty on K effective for these type measurements. Now, back in the early days, we didn't believe Monte Carlo calculations and said, somebody says, who knows that the geometry capability is correct? Myself and Dave Irving were the first ones to use a code called O5R, which was a code that generated a big pile of history tapes, which it then interpreted to try to find out what was going on in the system. And it had never been used for criticality safety calculations, so we came along and tried to use it. And so one of the questions was, is the geometry capability what it's supposed to be? Well, nowadays you'd think that's a stupid question to ask, right? Because you've got all these fancy codes that supposedly have been verified. But at this time, in Oak Ridge, Monte Carlo had not been used for criticality safety calculations. So here's one of the experiments we did: an annulus, okay, with a parallel pipette inside, shoved off to the side. And just to get again, two halves, put on the same kind of assembly procedure. Kept adding material to the parallel pipette on top until we got to delayed criticality. Another one, this has got, this is pretty dark. Same annulus again, with a cylindrical sample inside, 7-inch diameter cylinder inside a 15-inch OD annulus. Again, an odd geometry assembly. The next one, I'll show you a little picture of the diaphragm. Dave Irving saw this geometry, he said it's grotesque. Okay, and that was the name that stuck with this assembly. It had 700 pounds of enriched uranium on the diaphragm. Okay, so, or not 700 pounds, but maybe 300, some large number. So we had this 10,000 thick stainless steel diaphragm, and the way the thing was going to be assembled is that we had these uranium parts circled around on a ring, and it had a hole in the middle, in which we pushed up another piece. Now the question was, will this diaphragm rip, crack, sag, throw all these pieces into the middle? So we loaded it up with lead bricks and did all kinds of violent things to it, like started a tear to see if it would continue to tear. We actually took a 4x4 by 4-inch square steel block and slammed it into the diaphragm about here, penetrating it about halfway. The block didn't go through; it got stuck in the material, to see if we could cause this thing to fail. So we did a lot of crude tests to give us confidence that when we put this thing up with the hole in the middle, we could put the uranium around it safely. Next is the picture of this grotesque geometry. It's all this stuff stacked around in the ring, on a circle here, and here we have cylinders of different diameters, a parallel pipette with a cylinder on top of it, a plain parallel pipette over here, and the movable lower section, which came up in the middle here, had a cylindrical part, a parallel pipette part, and a hemispherical part. And so that was the greatest test of the geometry capability at that time, the O5R code. O5R code was such a difficult thing to measure because you had to manipulate all these history tapes. We then got Elliott Whiteside's and interesting developed Kino, which made it much more simple to interpret the calculations. We did some experiments with uranium, with polyethylene spaced between uranium plates. Again, 15-inch diameter plates with polyethylene interposed. Various thicknesses of polyethylene up to 1 inch. Did a lot of subcritical measurements with the source present by the so-called Rossi alpha technique, which measures the time distribution of the fluctuations of the fission chains excited by an external source, again using 2 detectors. Here's an experiment with the Kharkov-Walton accelerator. You see it here underneath the subcritical system, and this detector precariously hanging on cables above it. Very light detector and supported by its electrical cables. Pulsed the system, measured the time neutron decay as a function of time after the pulsing accelerator. In the early 60s, Whitehall came along and says, we have a casting problem. We want to cast some large annuli, and we also have the problem of handling them once they're cast. And so they came over to us with a special design problem they had, and we said, let's do it, just generalize it, and so that you guys won't come back next year or next month and ask us about another geometry. So we did a wide variety of annuli of different diameters. and different thicknesses with a wide variety of reflectors. And we did graphite reflectors with thicknesses from 1 inch up to 18 inches. And Shane is doing some work on benchmarking the thin reflected ones, the 1 and 2 inch reflected systems. But here's a picture of the polyethylene system. Now this is the handling problem. The handling problem is always the metal moderating systems like people and floors and walls. And so we were pushing the metal plus its low reflector into a hole in the top and side reflector to achieve delayed criticality. And what we always were worried about is that if this piece caught on the edge and lifted the top reflector and it slid down, you'd have a prompt criticality accident. Well, we always monitored on top with these little dial gauges that would measure a deflection of 1,000. When that thing was getting ready to go in this hole, we look at those gauges to see that it wasn't lifting the top reflector. At the very exact time we were doing this measurement, Livermore, in their critical facility, had a criticality safety accident doing exactly the same thing, pushing something into something, except it got caught on the edge. They had no monitoring. They lifted the top. When they got it up a little bit, it slid back down, and they had a prompt criticality. And we felt pretty good because we were thinking ahead and trying to prevent that from kind of happening. So we did these with graphite and polyethylene. Did experiments like take a uranium cylinder, metal cylinder, and put reflectors just on one side, which simulates what happens when this thing drops on the floor. A concern in the Y-12 plant. Next, we did some experiments with a sphere. Now, this sphere experiment came about. Gulf General Atomics wanted to measure the neutron spectrum as a function of energy, and so they said, can you build us a sphere near critical with a big reentrant hole in it, and we'll crash the beam of an electron linear accelerate into that and do time of flight measurements of the spectrum. So we built that assembly and sent it out to California with the vertical assembly machine, and they did those measurements. And when they returned it, we said, we got this nice sphere. It's rounded than Godiva was, so why don't we do some nice reactive physics experiments? So we filled the reentrant hole and put some other holes and had filler plugs so we could put counters and various things inside, and did a lot of reactive physics measurements with it. This is a picture of the sphere assembled. It's, at this particular assembly, it is 60 cents above the late critical, so when assembled, it's going on a few second reactor period, which means the power's going up a factor V every second or two. Pictures taken with the photographer not in the room, but the camera in the room. The next slide shows you the top assembly, top section. It was mounted on a ball and socket joint, like in your shoulder, so that this thing could flex. Okay, that was so that when it came down, it could find the correct position. This is the central section, mounted on 4 lightweight supports that were pinned to a uranium plug in the system, and these things could move in that direction, so the centerpiece could wobble. What you did is you put a level on here and adjusted this till it was level by adjusting the length of these various arms. It's a little alignment cone which assured that the top piece came down in the right spot. And now the bottom piece, this is on a rigid support connected to the lower half, and then you can't see it on top of this. This has an alignment cone to fit into the central piece. So you drop the top piece, and then you push up the bottom piece, lifting the top slightly. We did some, how am I doing on time?
Another 15 minutes.
Yeah. We did a lot of reactor mock-up experiments. They were kind of interesting. One of the first ones we did is for a space power reactor. This was basically a thin beryllium or graphite reflected assembly cooled with liquid metal. I think the design at that time was potassium. And so this was oxide fuel pins in a tube. There's a couple of the pellets assembled in a little support device, and then they would slide down into the tube, and you'd seal the tube. So that was the fuel for it. Here's a grid plate. This was one of the first grid plates made in Whitehall by the automatic machining, computer-controlled machining operation. And they told us that this costed $25 to make this plate. Another plate where we tried to cluster the fuel pins to try to see the effects of positioning of the fuel pins. Here's a picture of the core of beryllium and carbide reflected snap reactor mock-up. Here, all the fuel pins are in the core. The central fuel pin is left out, and this support stand is mounted to the bottom lift. It was again pushed up inside the top and side reflector. Here's a picture of it on the lift. The previous picture was with beryllium on the bottom. This is a picture with graphite on the bottom. For the lower lift partially pushed up with this on it. And here's the picture of the core and side reflector pushed into the bottom and core and bottom reflector pushed into part of the side reflector. And here's a picture of the total assembly with the top of the top graphite reflector on top of the side reflector. There were various holes though that we could go in and make various measurements. And again, in assembly, this thing worrying about, do we really hit the hole when we raise this thing up? We did a potassium reactivity coefficient measurement. We built up this calandria with the fuel pin locations, and we had two of them, one that had nothing in between the fuel pins and one that had potassium. And that was to measure the potassium reactivity coefficient to see what the effect on the core would be if it lost the potassium coolant. Here's a sketch of the beryllium assembly. Core, side reflector, top reflector, and bottom reflector. Bottom reflector and core again on the vertical lift. Here's a picture of the assembly with all the components. The lower reflector was made up of little blocks left over from a previous experiment related to what was called the Aircraft Nuclear Propulsion Project. Okay, which was put to rest by the Tower Shielding Facility when they discovered that you could put all the shielding you wanted between the core and the pilot, but the sky shine would scatter enough radiations to make it very unhealthy for the pilot. So we had all that material left over, and so we used some of that for the bottom and top reflector. Here's a picture. You can see the little blocks stacked in this aluminum can on top. Did a lot of measurements. Foil irradiation, just see we're putting little foils in adjacent to the fuel pins to measure distributions. Here's an axial fission rate distribution in the first assembly. What you worry about here, this is basically a power density distribution in the reactor. You like to have the power density flat so that there are no hot spots. Obviously in here, the hot spot would be here, a little cooler on the edges. Some more fission rates in the reflector, measuring with fission foils, and again, the cadmium ratio, which is basically the flux, total flux divided by the flux with cadmium around the foils. It shows that the spectrum is quite hard with this assembly. Health Physics Research Reactor was an interesting project that came along. There was a lot of studies going on related to dose measurements and health physics effect of the detonations over Japan. And the particular assembly they were considering was what was called a Little Boy, which is the uranium assembly, which was detonated 1,500 feet over one of the cities in Japan. And the idea behind this reactor was, let's build a reactor that has the same leakage spectrum as that device and put it up on a tower in Idaho. Not Idaho, it's a test site, Nevada test site, I'm sorry. 1,500 feet up in the air. And so this reactor was built at Oak Ridge and then taken to the tower. And I don't know if, I've never been on a 1,500-foot tower. I don't want to go up there. The people that were up there were saying is that them and the reactor would just sit there swaying in the wind. And so some sketch of the reactor. Basically, it's a set of plates stacked up and bolted together. Okay, circle of bolts, 9 bolts, and then three rod positions: mass adjustment rod, a burst rod, and a regulating rod. And the way the system worked was that you assembled it to delay critical. You set the reactivity with the burst rod out. The burst rod had about $1.02 reactivity worth. So you had the rod out, you adjusted everything to the reactivity you liked. You then took out the center section of safety block. This is roughly 100 kilograms, 20 of which are in this block, which could be lowered. This went down into this, we call safety tube, and I'll talk a little bit more about that in a minute. You then waited for the neutron population to die away, and you reassembled the thing without a source present. Okay, and then fired the burst rod in and waited for a prompt excursion to happen. Well, the prompt excursion was usually initiated by cosmic ray neutrons or some other, or the spontaneous fission source in the material. There was roughly 100 fissions per second in this assembly. You get roughly 1 spontaneous fission per second per kilogram. Well, you could wait sometimes up to 4 seconds before anything happened. And you'd say, I did put the rod in. It did, I heard it go in. Okay, and so then the burst would happen. And then what you heard when this thing, there's a lot of fission energy transferred to kinetic energy. And whenever you made a pulse with this thing, it sounded like you had a piece of metal on the floor and you hit it with a sledgehammer. Or this big clang. So you always would know the pulse really happened. Okay, next one. Well, now, when we started this, there were no experiments with 10% uranium and molybdenum. And so we did some basic experiments with uranium molybdenum alloy of 10 weight percent, 93% enrichment, just like the material for the core. People have done some previous experiments with 3 weight percent. And so we did some basic experiments where we, criticality safety experiments, determined what the critical mass was. We took out the center section to simulate a piece of the safety block coming out and did various measurements related to verifying the calculation methods for the design of the reactor. Next, we built the reactor. This shows the reactor plates and some of its structure and the support tube. The plates had different color. They were nickel coated to keep oxidation down and keep your facility clean. They weren't sure how to put the nickel plating on. They had 3 different methods, so they put it on 3 different ways. That's why these have different colors. Well, all 3 turned out to work okay. You'll notice these bolts were screwed into the bottom. See a piece of them sticking out? Okay, next slide. This is the full assembly. Here you see the safety tube on. Now, what the safety tube is for is if this thing falls on the floor, you don't drive the safety block up inside and get the 100 kilograms assembled. So you have this steel device in here which prevents that. An interesting story about the bolts, we went up to 2 times 10 to the 17th this experiment, and when we come to take the core apart, we found out we couldn't unscrew the bolts. Another interesting story about this experiment was that we were sitting over the one ridge over from Y12, and we're making prompt criticality excursions that ultimately got up to peak powers of 100,000 megawatts. And we thought that the hill between us and Y12 would keep Y12 happy. Well, as we got up in yield, we set one off, and what it did is that the sky shine came down on the Y12 plan, and the criticality safety alarms in Y12 then were 3 out of 3. All criticality safety alarms in all buildings went off simultaneously. So he got a very interesting call from the plant superintendent. And the outshot of it was that, hey, when you do that again, tell us. So then we did it again. We would call him up on the phone and say, hey, look, we're going to shoot one. Bypass all your evacuation alarms, and we'll call you back when it's over. And so if you stood in the next valley with a health physics radiation instrument, a little cutie pie, you would see the needle peg. I mean, it would just hit the top peg and come back down. And so did the criticality safety alarms responded accordingly. This is a picture of the whole system, all of this stuff up on drives and safety instrumentation and monitoring channels, and these are ionization chambers and moderators. And this whole thing went to Nevada with some of my coworkers and was put up on a tower, and they made pulses, and they did all these radiation studies with different Japanese-style housing spread out on the desert below at different distances. The next one, the Aberdeen pulse reactor. They wanted a reactor at Aberdeen for doing kind of military studies, and so they came to us and they said, well, we'd like a reactor. And we said, well, can we do something a little different than last time? Can we test this thing to destruction? And they said, sure, we can do that. It just means we have to build a new core. So that's an interesting part of this experiment. So here's the Aberdeen reactor, a little similar. Now you see there's not too much variation in the plating. But here's a picture with a scintillation counter nearby in the core. Now in this measurement we did something different from the previous ones. We had Sandia come in and put little electromagnetic coils of a millimeter or so away from the fuel plates. And so what happens when you make a pulse, this thing sort of rings like a bell. It vibrates with a nice sinusoidal motion. At lower amplitudes, and at higher amplitudes it gets into some wild higher harmonics by coming. So we proceeded to make pulses with this thing. Now, this one had a very interesting feature. It had a thermocouple on the surface held by some crude mechanical holder that once we got to a certain pulse rate, it broke the little screw and threw the thermocouple on the floor or hanging out wherever. There was a requirement to operate, so in between pulses we had to go in and put that thing back. First we had to drill out, the dose was high, and we're going along on our merry way towards our destructive accident. Everybody in the building had gotten their quarterly radiation dose limit, including the secretary, and we said this was the last one. And so show you a little bit of data now. Here's the fission rate as a function of time, and then here's the mechanical displacement as a function of time. You can see it's sitting there doing this. Okay. When we got to the last pulse, we said, okay, this is it. And so we put enough reactivity in to raise the temperature almost 1,000 degrees in a matter of a few hundred microseconds or so. The pulse is produced in less than 50 microseconds, but it takes a while to heat up. We ran down the control room for this thing was in one cell and the reactor was in another, and so we ran over it, and always after a pulse, and looked through the water windows to see what we could see. And we looked through here. It was red hot. Okay? And Dixon Callahan, my boss, said, "What did you do, John?" The first time I ever saw him get excited. I said, "Well, we planned to do this. This was the last one." So that was interesting. Well, we couldn't get it apart either. Here shows some of the cracks we put in the core. The actual core pieces came out and hit these little displacement gauges on the first vibration. We had to break some of the bolts, and the way you break one of these bolts, 1-inch Umari bolts, you take a 15-foot long pole with a socket on it, put two guys on the end of it, and you push. Okay? So then we could get the core apart. Now, we tried to do something different here by putting nuts on the bottom of the bolts instead of threading them into uranium molybdenum. Well, that didn't quite work either, but subsequent to that, the reactors had bolts on the bottom. And here you see some quite large cracks, and For you engineering types, I don't know, this was my first experience with stress corrosion cracking. Okay, we took these bolts, and they looked fine, except they were broke here, and we put them on a table. And then we watched them, and guess what? Spiral cracks begin to appear, okay, like on the barber pole, and eventually they just fell apart. Okay, another interesting, how am I doing on time, Larry? If I started late.
Another 5 minutes.
Okay, I think I can make it. We did a mock-up for Uratum Institute of a reactor that was supposed to produce thermal neutrons cold neutrons from a moderator, sort of like SNS is going to make for the SNS project. Only they wanted to do it with a reactor that was pulsed by a movable reflector. And so it was uranium metal in the iron matrix, 2 beryllium rods, big iron reflector with 2 thermal polyethylene regions. What in actual practice these would have been some cold liquid nitrogen temperature devices to get the neutron energy down, and then try to look in beam tubes at what came out. They were going to get a higher average. They were going to get a higher flux at the time you wanted it by pulsing it and by rotating this reflector. And so we first did. Here's a sketch of the full system, and I'll talk a little bit more about this rotor. Here's a piece of beryllium insert in a titanium aluminum titanium vanadium alloy rotor with a small motor here, 75 horsepower motor. And then here's the core and the fuel pins that was pushed up, and then this thing was rotated. And as the beryllium reflector got to its maximum reactivity, we pulsed the Cockcroft-Walton accelerator so that a pulse would be made at the exact time. You wanted the flux to go up at the time this thing was at its maximum reactivity position. So it had no source except accelerated, and it was pulsed on. So here's the static mock-up of the thing, same vertical tables. Now you see the core iron matrix with its fuel elements and the side reflector. And here a crude rotating arm simulate reactivity effects for the beryllium rotating reflector. The next one shows the installation of this thing. We didn't know about rotation at all, had no experience, and so we said, well, who knows about rotation? We said, well, the guys at K25 got the world rotating over there, so we'll go talk to them. So they sat down and designed this rotor. It had the beryllium down here. It was a titanium vanadium alloy. It had a uranium counterweight in the back because it was shorter in the back, because you don't want the backside to come around and make a high reactivity when it goes by the core. You just want the beryllium part to do that. So they took this thing and told us how to make it. We didn't have to do any research. They said, we'll just build it. We'll test it at K25. When they tested it at K25, they just put piles of sandbags up around in some area, put this 75 horsepower motor they happened to be laying around with the bearings and everything, and ran the test. And my understanding is that this thing pumped the sand out of the sandbags. Okay, and the reason we knew that is when it came to us, the front side of this was all pitted from sand that had been knocking around in this little facility. Actually, you wouldn't believe it, but the whole testing and installation and building of that thing cost only $10,000. An interesting happened when we put it in the assembly machine before we even got to the critical experiments. We said, well, let's close this up and rotate it. Okay, then we learned about friction. Okay, the temperature went up 40 degrees centigrade per minute. Okay, so that was intolerable. And so we proceeded by putting some cooling tubes on the back. But the thing that really made it happen was that we used helium gas inside the shroud so that the rotor was moving in helium. And it completely solved the temperature problem. And here's this little 75 horsepower motor, and that's a big thing. There's an interesting story I'll tell about that. What happens with this 75 horsepower motor, it kind of loads your electrical system down. And this Cockcroft-Walton accelerator had something called a pinning iron source that we were pulsing on just for a few microseconds. And what this motor was doing was that every 960 revolutions, it missed one. It didn't keep up with the 60 cycle because of the load. And so instead of getting 960 in a certain time period, we got 959. Well, every once in a while, when we got that 959, the iron source came on steady. Instead of a microsecond pulse, we got a steady state pulse. And of course, the power shot up, straight up, scrammed everything. We worked with the physics division here who invented the iron source for 2 months to try to solve the problem. Had no solution, but it went away one day. And we did the measurements in a month, and it never came back, and we never knew why. Here's a picture of the system with the top reflector with the polyethylene thermal poles mounted against here. What we did is the Cockcroft-Walton accelerator was mounted sort of on this side of the shroud, same side as the motor, and when the beryllium got to the very middle of its maximum reactivity position, the pulse would come on. Here's a picture of a young scientist. 40 years ago. That happens to be me in the back here. That's all I have. Any questions?
You did those 05R validation studies. I mean, was it just the one number?
That's it. That's it.
What did you vary it? I mean, to make sure it wasn't compensating errors or something, to have a lot of different arrangements?
Of material, you mean?
You know, when you were doing the 05R test, did you move all those little pieces around?
Well, we moved until we got them critical and then left them there. We had that in the other two assemblies and some of the other ones. See, back then, cross-sections were an interesting thing. My first experience with cross-sections was in 1953. We were doing some reactor design calculations, so we went to Brookhaven, talked to the cross-section experts at the center. We want to know what the cross-section of zirconium or something. And you'd open the barn book, and there would be some values at thermal and some values at 1 MeV. And this was with Jack Harvey, who's the world's expert. We said, well, what about all the way in between? And he'd say, well, it sort of went like that. And we take a pencil and draw it like that. Okay? And then we make 25 group cross-sections. and you had to do that for half the elements, you know, because there was nothing there. That's well.
You make the Rossi alpha measurements in the frequency domain?
No, back then we did in the time domain. Now, an interesting thing about the Rossi alpha measurements, we did Rossi alpha measurements up to 90 cents above delayed criticality. Rossi alpha measurements measures the time decay of the prompt neutrons. And as long as you're below prompt critical, you can measure that. Now, the flux is going up like hell, and you can't stay assembled too long. You have to stop your measurement, shut it down, and then start it again, cycle it. But you can actually measure prompt neutron decay all the way up to prompt criticality, even though you're going off on a 2-second reactor period with the delayed neutrons. These experiments were done quite precisely, and I think they're really ripe for benchmark experiments, and some of that work is going on now, but there's a whole wide variety of experiments that could be benchmarked to much higher accuracy than most things have been done. We appreciate what Shane is going to do. Hopefully there'll be people who follow this. There's 10 projects out there at least.
Are there any other questions for Dr. Mihalczo? Okay, let's give him a round. And remember also that we have refreshments downstairs, and would you like to join us, John, and have a cookie and a Coke and so on as well?
Sure.
Okay, that concludes today's seminar, and thank you for coming.
You said seminar, it's going to report.
Hello? Yeah.
Hey, John.